Okay, there you go. It's working.
Okay, good morning, everybody. Thanks so much for joining this webinar in present and on Zoom. So it's my great pleasure to introduce our speaker today. He's actually from next door, Jérôme Bouvier. He's a research director from IPAG, Institut de Physique et Astrophysique et Planétologie. And he got his PhD in 1987 in the University of Paris 7. It is now Sorbonne University.
Yeah.
And 1 year later, he joined the CNRS as a CNRS researcher. And in 1992, he came to Grenoble. So he's already since 32 years around in Grenoble, so very long. His research focused on observation, combining observations. So he went to Chile to look at, to use the very large telescopes there. It's called the European Observatory, La Silla, and also the observatories in Hawaii. So it's called the Canada France Hawaii Telescope. And he joins these observations of young stars with modeling. And this is what he will tell us about. His research was awarded several times. He got the CNRS Silver Medal in 2011, as well as an ANR and lately also an ERC Award, advanced grant that has just finished. He's also very active in actually NGO, bringing research to citizens through NGOs. And he's very active in this topic. And I'm very happy that he could make it today, despite the bad weather. And I'm looking forward to his talk. Thanks so much.
Thank you. Thank you for the introduction. Thank you for the invitation. Thank you for being here. I understand you work on the very, very, very small things. We work on the very, very, very large stuff, the universe. So we will meet at the extremes, I guess. I'm happy to be here. I've been here in Grenoble for 32 years. That's the first time I come at ESRF. So I'm glad to be here and to present the work we've been doing, or the status of what we know about the formation of stars and planets, and also on exoplanets, which is kind of a new chapter in astrophysics. So I apologize. This is a public conference, so it's intended for the wide public. So you don't need any physical background and even less astrophysical background. So I apologize to the physicists who might find that very, very simple, what I'm going to show. And also, it's the first time I give it in English. Usually I give it in French in festivals and so on. So I might be missing some words, but okay, you will apologize. I apologize for that in advance. So the outline of the talk is this one. So I will first give a few definitions on the objects we will be dealing with, the stars and planets, what the difference, what are they, and so on. And then I'll go to how do stars form. So we have a star formation theory, which is validated so far by observations. So I'll show both the theory and observations and numerical simulations. And then how do planets form around stars? The two processes go together. I mean, stars form, there are protostars, and planets form immediately, nearly at the same time in astrophysical timescales. And then I'll go to exoplanets. I tell you what the current status of exoplanet research. So exoplanets are planets orbiting stars others than our sun. And then I will conclude with by mentioning what are the current challenges we are facing and how we try to address them. So a few definitions on galaxies, stars, and planets. So the content of the universe. So the universe is filled with galaxies. Actually, there are hundreds of billions of galaxies in the universe. In this image, what you see is the James Webb Space Telescope's deep field, so that the deepest image of the universe ever obtained. It goes back to 13 billion years back, so at the very beginning of the galaxy formation. So most of these objects are galaxies. Oh, sorry for the laser. These are stars. The bright ones are stars. Okay, the star-like shape is not from the stars themselves, they are from the telescope optics. But all the other objects are galaxies in this image. So indeed, when you look far in the universe, and even in our galactic neighborhood, I would say you see galaxies everywhere. So galaxies, they consist of stars, of course, but also of gas and dust, and we'll be mostly interested by gas and dust because that's from gas and dust that stars form actually before being stars. And each galaxy hosts hundreds of billion stars. And this is a galaxy which in our vocabulary we call a spiral galaxy. You see the spiral arms. Most star formation goes along the arms. And our galaxy, if we could lift off and go beyond our galaxy, we would see a galaxy like this if we were able to go out of it. But of course, we are not able to go out of it, but this is what would our galaxy look like. And this is our location in the galaxy, which is fairly, well, not remarkable at all. I mean, this is the center of the galaxy with the black hole at the center. And this is the periphery, and we are about 2/3 from the center toward the periphery. This bright star is not the sun. The sun is a very average star in the galaxy. This is a very giant star. So we are somewhere there. And of course, this is an artist representation of the galaxy. So no particular location for us in the galaxy. Since we are within the galaxy, we don't see it from outside, but we see it from inside. And what we see is the Milky Way. And the Milky Way is simply when you look at the galaxy is a disk, it's flat. So when you look through the disk, you see a lot of stars. You see thousands of stars. And it looks like a bright lane in the sky. And this is the Milky Way that we see at night. And if you look in the perpendicular direction through the galactic poles, there are fewer stars, and therefore it's much darker. So the Milky Way is just the trace of the galactic disk on the sky. And that's what we see from our galaxy. So the sun is an ordinary star, but it's our star. So and it's very close. So we can learn a lot from this star. So we can define a star as a ball of hot gas, that's called plasma. For the sun, the surface temperature is 6,000 degrees, and the temperature at the center of the sun is 15 million degrees. And you need these temperatures to have the nuclear reactions that convert hydrogen in helium, that produces energy, and this energy which is produced in the core of the sun is transported to the surface layers, and then it's emitted as light at the surface of the sun. So that's because you have this nuclear reaction at the center that the sun radiates, and it's a star. The chemical composition of the sun is like most objects in the universe. That's first hydrogen, and then a little bit of helium. And these two elements were created during the Big Bang, helium and hydrogen, that the only two plus a little bit of lithium, but okay. And only 0.2% of the sun material is what we call in astronomy metals. Chemists would not call that metal, but these are all the other elements that you know. Nitrogen, oxygen, carbon, everything else is only 0.2% of the sun content. And that's what the Earth is made of. That's what we are made of. And these elements, they are created within the stars. At the beginning of the universe, there is only hydrogen and helium. And then little by little, the stars transform these two very simple elements to more complex elements, all the metals we are made of. And that's why some people say we are stellar dust, because all the atoms that we are made of were built within the stars through these nuclear reactions. The solar system, so we have one star, the sun, and 8 planets. There used to be 9, but Pluto has been retrograded. I don't know if you can say that, like 10 years ago, because it's a big rock, and there are thousands of big rocks like Pluto's in the solar system. There are remnants of the planet formation epochs 5 billion years ago. But if we classify Pluto as a planet, we should classify thousands of other objects. So it's not feasible. So we retain now only 8 planets. So the 4 rocky planets with the rocky surfaces, so Mercury, Venus, Earth, and Mars, and the 4 giant planets that are mostly gaseous planets, Jupiter, Saturn, Uranus, and Neptune. And here the sizes are to scale. So you see the Earth is very small compared to Jupiter and even more to the Sun. But the distances, of course, are not respected. The true distances, so the distance between the Earth and the Sun is 150,000 kilometers, sorry, English, which corresponds to 8 minutes for the light to travel from the Sun to the Earth. So, and the full solar system is like 6 light hours. So it takes 6 hours for the light to go from the Sun to Neptune, for instance. But then the next star, the closest star to our Sun, is 4.2 light years away. So it's much further away. So the solar system is really our garden. And the first star is far, far, far away from. So there is a lot of empty space in the galaxy between stars. Okay, what is a star? What is the difference between a star and a planet? Probably you know that, but a star, as I said, is a sphere of hot gas, plasma, that produces its own energy through nuclear reaction at the center of the object. And for this to happen, the central temperature must be larger than 5 million degrees, 15 million degrees in the Sun. It has to be larger than 5 million degrees, and only massive objects reach this temperature. You have to have a mass which is larger than 75 times Jupiter masses to produce this temperature that lead to the nuclear reaction. So every object that forms that has a mass larger than 75 Jupiter masses will become a star because it produces nuclear reactions. On the other hand, planets are much less massive. And indeed, they are too low mass to produce nuclear reactions. They do have some thermal energy. Of course, the center of the Earth and other planets is hot, but it's a few thousand degrees. It's not a few million degrees. And therefore, planets do not produce nuclear energy, and therefore they do not radiate. They just reflect the light of the star. They are the Sun in our case. They are eliminated by. And this limit for planets is so you can have very low mass planets, and the maximum mass for a planet is 13 Jupiter masses. So there is a gap. You notice there is a gap between 13 Jupiter masses and 75 Jupiter masses, and this is kind of a twilight zone where we do have astrophysical objects that we call brown dwarfs. These are failed stars, if you wish, or yeah, these are objects that produce nuclear reactions for a limited amount of time, a very limited amount of time, and therefore they are not considered as stars because they are not stable. Stars are stable because the nuclear reaction produces energy that balance gravity. Therefore, they are in a stable configuration for most of their life. I'm not going to talk about brown dwarfs. We can come back to that later if you'd like. So how do stars form in the galaxy? Well, the galaxy, as I said, they consist of stars, gas, and dust. And actually, it's in the gas and dust that make this beautiful nebulae that we see. This is a telescope image of one of the nebulae of our galaxy. And this is the site of the star formation. That's where stars are born. Maybe you know this one. That's the Orion constellation, which we can very well see. We are in December, so at the sunset and in all the night, actually, we can see Orion rising above Beldon. And you can notice it with this large rectangle and these 3 aligned stars. So it's very easy to point in the sky. And then you have, again, 3 stars aligned vertically here. And on the middle star, you have this beautiful Orion Nebula, which has an age of 1 million years, and 1 million years on our scale is equivalent to 2 days. If a star were to live 80 years, let's say 1 million years would correspond to 2 days. So these are regions, very, very young regions, where we do find this newly born star that we study to understand the star formation process. And if you look closer in this nebula, you have these bright regions, because it's gas which is illuminated by bright stars. We don't see the star, but they are within the gas, and they illuminate the gas, hence the colors. But there are also dark regions, and that's in the dark regions, actually, that the stars are going to form. And these dark regions, what are they? They are clouds of gas, opaque gas. This is molecular hydrogen, and mixed with the gas, there is always some dust, and the dust is opaque. The gas is transparent, but the dust doesn't let the light go through. And here, for instance, you see one of these, what we call dark cloud. Behind you have the Milky Way, so you see a lot of stars, except that here, the dust in the cloud intercept the light and absorb the light, and you can't see behind. And this is the same in front of a nebula, of a gaseous nebula. And these are very, very cold medium, like a 10K, so minus 263 Celsius. The density is extremely small. It's a 1/10 of a billion of gram per square centimeter. So I think, you correct me if I'm wrong, but I think that's emptier than the best empty vacuum we can do in our labs. Maybe you do better here, I'm not sure. But it's very, very shallow, very low density, very cold, but it is still very massive, like equivalent to 10 times the mass of the sun, because it's extremely large. It's 1 light year, typically. So it contains a lot of mass. And then this is within these clouds that the star will form. And this is a beautiful image from the Hubble Space Telescope. So it was some time ago, where you see this dark cloud, you see the background nebula, and you see these 3 stars that just formed out of this dark cloud. So it's, I like this image because it looks like a nest with a few eggs in it. So this is the nest of the star formation process, and these are the newly born stars. And these protostars, as we call them, we can, of course, analyze their light, and we find that for their age is 100,000 years, so it's extremely, extremely young. And their temperature is already 100,000 K in the core, and the density is 100 grams per cubic centimeter. So there are already stars, very young stars, but stars. And the whole challenge of understanding star formation is to understand how you go from a very cold and low density gas cloud to a very dense and very hot protostar. And in order, so this is the issue we have to address. And in order to address this issue, we have a theory, which is physics, gravity mostly. Gravity is the main, gravitation, the main force that drives star and planet formation, actually, at least star formation. We have numerical simulations, I'll show one, and we have observations to see whether our predictions are correct. So I will describe here the main processes that happen during star formation. These dark clouds, so they are bright now, but these correspond to the dark clouds I was showing before. These dark clouds, because they are very large, very cold, they are unstable. So if they are perturbed, and usually they are perturbed by exploding supernova in the galaxy, that triggers shock wave within the galaxy. And when the shock wave hits the cloud, then the clouds, which is unstable, start to collapse. And it will collapse under its own gravity, and nothing can stop the collapse. So it will collapse. And as it collapses, the gas is compressed. And as you know, when the gas is compressed, it starts to heat up. So the star will be compressed more and more, and it heats up to a few thousand degrees, few 10,000 degrees, a few 100,000 degrees. And that's just by compression of the gas that you get the central protostar. But there are two other processes occurring simultaneously. The initial cloud is rotating. Everything is rotating in the universe, the Earth in 24 hours, the Sun in 26 days, the Sun around the galaxy in 220 million years. And these gas clouds, they are also rotating very slowly because they are very large. But as they contract, because the angular momentum is conserved, that's a physical law, then they will spin up and rotate much more quickly. And they rotate so quickly that they reach a breakup velocity and they fragment. So one cloud like that will give rise to several fragments. And each of these fragments will continue to contract, and each of these fragments will form a star. So from one cloud, you don't form one star, you form a number of stars. It could be 3 stars, could be 1,000 stars. It depends on the initial mass of the cloud. Okay, so you form a stellar cluster, in fact, most of the time. And the fact that rotation is still there in the fragments also has another consequence. It's the formation of a disk around the protostar, because of the centrifugal force, all the material cannot fall in the center. Part of the material is deflected toward the edge, and therefore it forms a disk around the protostar. That's what we call a circumstellar disk, circumstellar around the star. And this disk is formed from the initial material, which is gas and dust. And that's important, of course, because it's in this disk that the planets will form later. But I'll come to the planet formation later. So that's the concepts we have, that's the theory we have. So we can work out the numbers with the gravity and the force, centrifugal forces, fragmentation, and so on, to compute the properties of the protostars and their circumstellar disk. So this is just a graphical representation of the same process. So you have a rotating cloud that fragments, and each fragment forms a protostar surrounded by a disk. So in order to validate or invalidate the predictions, then we go and observe these young star-forming regions. So we use a number of instruments. I've selected a few here. There are many more. But we observe from space in part, so with the Hubble Space Telescope, which has been fantastic for the last 30 years, with the new James Webb Telescope, which provides incredible images and spectra as well, and also with less well-known but very helpful telescope for us, infrared space telescopes. And infrared, we go to the infrared range because we are studying cold medium. The circumstellar disks are cold, and it's better to investigate them in the infrared and even in the radio wavelengths than in the optical. So these are a few of the space telescopes we use, but we also observe from Earth, obviously. These are the 4 very large telescopes, European telescopes in Chile and in the Paranal mountain in the Atacama Desert. So we go high and we go dry because we want to have as few atmosphere above our telescope and very low water content, because all this destroy the images and the signal that comes from the stars. So that's where we go there to put the telescope. So this is the biggest facility on Earth currently, especially because you can combine the 4 telescopes to have the equivalent of one extremely large telescope. And then much closer to us here on the Plateau de Bure, so next to in the Dévoluy, not very far from Grenoble, we have this interferometer, which is a radio telescope, so radio antennas. There are now 10 antennas, and these are extremely useful to investigate the circumstellar disks, for instance. The next step will be this extremely large telescope that Europe is building, very close to the very large telescope. So, you know, we had the very large telescope. Now we will have the extremely large telescope. The next one will be the hugely worse telescope. I don't know. You will have to find a name, but this one at least is being built. And there is even a webcam. You can go on the website and see the advancement of the works here. It will be operational in 4 years from now. And you can see the size. It's a 39-meter telescope. So far, the largest telescope on Earth is 11 meters, I think, and we'll go from 11 to 39. So it's a giant leap, let's say. And you can see the size of the individuals. And these are big cars, I can tell you, these are big cars, but it looks very small compared to the telescope. And okay, we'll have certainly a very nice instrument to go further with this new telescope. So with this telescope, we investigate these star forming regions, and this is a recent James Webb Space Telescope image. This is a stellar cluster that just formed, so you have hundreds, probably thousands of stars, and you see the residuals of the dark cloud. When the star forms, they irradiate on the cloud, and they disperse the cloud. They blow away the cloud. So you see they have drilled a hole here, but you still have this remnant of the original cloud of gas and dust that gave birth to this stellar cluster. And statistically, since we measure how many stars, young stars we have in the galaxy, statistically, we know that every year, the equivalent of 3 suns are born every year in the galaxy. So that the star formation rate in the galaxy. So now we put that in our computers, and this is a simulation of the formation of a stellar cluster. So at the beginning, you have this gas cloud. So this is only gas and dust. And the color scale is density. So these are the densest region. This is the dimension. So here you have, well, you have a few light years. And here is the time. So you have 200,000 years here. And you see that the cloud is collapsing. And so you have denser region at the center. And in this denser region, you will see appearing white dots. And white dots are stars that have been forming from the contraction of the cloud. And you see it's a very dynamical process. It's rotating, it's interacting. You know, so there are a lot of gravitational interactions. Some stars are ejected, some systems with their disk are ejected. And these are numerical simulations that are done on the most powerful computers, and it takes usually a few months to do that. You see here a circumstellar disk with a star. So that's putting the properties of the dark clouds and let them collapsing yields this formation of a number of stars. You see here we form 50 stars that are strongly interacting. There are new simulations where the interactions are not that strong, but still the concept remains. That's the contraction and the interaction of the star that eventually leads from this initial cloud to this stellar cluster. And indeed, so these are the predictions from numerical simulation. When we observe this young stellar region, this is one of these clouds that just form stars in Ophiuchus constellation. And you see everything that I described. You can see still these dark clouds. A supernova exploded in this region on the bottom right corner here. So the supernova is there, and a shock wave came across the cloud in this direction. So it forms stars all the way here, and it's reaching, and you see this kind of cometary tails, as we call them. This is the shock wave going through these dark clouds, and these dark clouds will form stars within a few 10,000 or 100,000 years, but they have not formed stars yet. While here you have already formed stars, and you can see these spiral structures here that are the remnants of the collapsing cloud, and stars embedded still in the gas and in their cocoon, actually, that led to their formation. So everything we observe actually corresponds to what is predicted. So that kind of validates the concepts and the numerical simulation we can do on star formation. Now, if you look closer, if you take one star and look closer, what do you see actually in the immediate environment of the star? That's what you see actually. These are actual images taken again. These were the first images taken by the Hubble Space Telescope 20 years ago, a bit more, 25 years ago, of circumstellar disks. What you see here are circumstellar disks. And why do you see them like that? That's because you look at the disk through the disk plane, and the disk plane is opaque. So you cannot see the star, which is in the center. The star is hidden by the disk. The star would be here. And the dark line is the disk midplane. And what you see is the upper part and lower atmosphere of the disk, which is illuminated by the central star. So it looks like a diabolo. See, you see that here, this one, that one. And this is what is represented here, except that we are looking through this opaque plane, which act as a natural coronagraph. We call that a coronagraph when we hide the star to see what is around the star. So this is a natural coronagraph, and that was the first images of circumstellar disk, which confirmed the prediction that disks should form around newly born stars, and all newly born stars, all stars form with circumstellar disks. And these disks have at the size of the solar system, so they are prone to form planets, and I will come to that in a moment. So what really revolutionized the study of disk is this new facility, that's ALMA. So it's like the Plateau de Bure facility, except instead of 10 antennas, you have 64 antennas in the Atacama Desert at an altitude of 5,000 meters. So it's extremely pure sky, extremely good images. And from this kind of facilities, which is absolutely huge, and again, that's a European, American, and Japanese facility. It was too expensive just for the Europeans or just for the Americans. So for the first time, we had to join all the communities, well, major communities at least, to build that. And this is the very first image from this facility. This is the image of a circumstellar disk around a young star. And now we are in the radio wavelengths. So in the radio wavelengths, we don't need coronagraph because the star is not very bright in the radio domain. So we can clearly see the disk around the star. And the surprise with this level of details that we had never had before, the surprise is that the disk is not at all homogeneous. It's not a continuous disk like a CD, you know, not at all. You can see a lot of gaps, actually. You can see some structures in the disk, a lot of gaps. So what is bright is gas and dust, and what is darker is a lack of gas and dust. So there are structure in the disk, and that was the first time it was seen thanks to this ALMA facility. Now we have another facility that we built in our lab in Grenoble at IPAG, which is adaptive optics system. So first we put a small patch to hide the star. So it's a coronagraph, it's a mechanical coronagraph. So we are not outshined by the star, so we can see what is around. And adaptive optics means that we have mirrors that are flexible mirrors that moves as fast as the atmosphere and in an opposite way. So you can correct the atmospheric turbulence from the ground. So it's as if you were observing from space, nearly, depending on the quality of the adaptive optics system. So that's one of our specialty at IPAG. And these are images we got with this, so it's on the Very Large Telescope in Chile. And these are examples of disks. And you see that every time we look at disks around these young stars, we do see a lot of structure. That can be spiral arms. These are gaps. Sometimes the disks are warped. You have a lot of structures. And we believe that these structures are the results of the gravitational interaction between the disk and forming planets within the disk. So if you form planets that is relatively massive objects within the disks, then, as I'll show in a moment, you can create this substructure just by gravitational interaction. So how do planets form in these disks? Well, the concept is relatively simple. It's very simple even. Since the disk is made of gas and dust, the dust, of course, is very, very small at the beginning. It's a micron size grain. But since they are all together in the disk, rotating around the star, they merge, and they merge to form a millimeter grain dust. And then these merge again to form pebbles. And then by merging, they form rocks. And these rocks eventually forms protoplanets. And by impact of asteroids that have been formed in the same way, they eventually form planets in the disk. So it's by dust aggregation and merging, accretion, that planet form on a time scale of a few million years. Oops, sorry. On a time scale of a few million years, which is very, very, very short in a star lifetime. The sun, for instance, lives for 10 billion years. So you see 1 million years is equivalent to, as I say, like 2 days. So very quickly you form the protostar and the planets in the disk around. So this is the idea. So it's the growth of dust grains from millimeter size to kilometer size by merging and aggregation. So the idea is that by gravitation, these dust grains are going in the disk midplane just through gravity, the gravity pull of the star actually. And then when you have all these dust grains in one plane, then they merge and they form this kind of planet that is emerged. Some of them, many of them, thousands of them are still in our solar system because they have not merged into a planet. So that's the kind of rocks that Pluto is made of, for instance. So you can form two types of planets, telluric or gaseous planets. Telluric planets, you just aggregate dust. The Earth, for instance, and Venus and Mars and Mercury will form like that. But if you continue to do that, and if you reach 15 times the Earth mass, then the protoplanet is massive enough to attract the gas from the disk. And therefore, you have a solid rocky core. You have a solid core of at least 15 solar masses, which will attract this gaseous atmosphere from the disk. And then you have a gaseous planet, which has a rocky core and a very massive, much more massive gaseous envelope. That's why you have two different types of planets. And now I will speak about exoplanets. We have everything in between an Earth and a Jupiter. It's a continuum of planetary masses. So on the right side, you have a numerical simulation of what happens when a planet forms. So the planet forming the disk, we are looking at the system from the top. The star is here. And here a Jupiter mass planet is forming in the disk. So it triggers this spiral arm that we have seen with the adaptive optic systems. And then when it becomes massive enough, it's not the right movie, okay? It doesn't matter. When it becomes massive enough, it creates a gap. It will remove, that's illustrated here, it will remove the gas immediately when it has formed and has a few Jupiter masses, it will remove the gas immediately in the surrounding. And that's these gaps that we do see in disks. This is the first discovery of a nascent planet. So that's by a colleague in Grenoble here. That is with the ALMA facility 3 years ago. So this is a young star. So we don't see the star again because we are in the radio wavelengths. We do see the disk, or what remains of the disk. And here, this dot is a planet, a protoplanet that has formed from the disk that has created the gas. And if you zoom on this planet, or protoplanet, you can see that even this object is surrounded by gas. So there is probably a circumplanetary disk. So it's still gas and dust around the planet, which is still forming. So either this gas will be accreted by the object and it will be becoming a very massive planet. For the moment, it has like 4 Jupiter masses. Or it will create moons, satellites around this giant planet, like Saturn and Jupiter have tens of moons. And this is a direct image this time that corroborates all the predictions that we have. So this is a movie. Okay, I have to start here. This is an artist movie from the European Southern Observatory, showing what we would see if we were able to go and visit this. We would see the young star here, the disk, gas and dust, a lot of small rocks everywhere, forming planets here. And the disk is slowly actually created by the star. So in a few million years, the disk will disappear, but planets have time to form in the disk before it disappears. Blown away also. And this is this is kind of an advertisement because my ERC project is called SPEEDY. It's a star planets inner disk interaction. So I was working for the last year with 8 young people, 3 PhDs and 5 postdocs. We have been working for 7 years on how the disk interact with the star. And it's a complex process which is mediated by the magnetic field of the star. The star has a strong magnetic field, so we have magnetospheric accretion. So this material is slowly going to the star through the magnetic field lines. And we discovered, and that was the CNRS news a few months ago, we discovered the first inner planet in these disks very close to the star. That's what we were looking for. So that was the goal of the SPEEDY project. If you want to know more, there is a website on the SPEEDY project that gives more details. Okay, so I turn to exoplanets. What do we know about exoplanets? Because planets have formed around the sun, obviously, but they form everywhere, also in the galaxy. And this is the detection rate of exoplanets. So starting, the first one was in 1995, the first one around a non-degenerated star, a star like the sun, let's say. And then you see the number of exoplanets. Today, in December, today we know nearly 6,000 confirmed exoplanets, and there are thousands of additional candidates, which will likely be confirmed in the months or years to come. And you see this increase of planet detection, which is due to the improvement of the techniques and the instruments. You can see it's not continued. There are steps here, steps there, and these steps correspond to the new instruments coming in operation to look at, well, not to look because we don't see them most of the time, but to detect this planet. So how do we do that? Well, the first planet was discovered in 1995. It's called 51 PEG B. B is for the planet, is B, and the first one, C for the second planet of the system, and so on. 51 PEG is the star itself. And these two colleagues, Michel Mayer and Didier Queloz, Swiss astronomers in Geneva, they have used this telescope in Observatoire de Haute-Provence, close to Fort Calquier, to discover the first exoplanet. And they won, of course, the Nobel Prize for that a few years later. As you see, you have to be patient. If you are still expecting the Nobel Prize, you should not desperate. It comes very late, usually. So how did they do that? Well, we have several techniques to detect exoplanets. The one they used and the one that was the most successful in the first 2 decades, let's see, was the radial velocity methods from Doppler effect. Because when a planet orbits a star, actually the two bodies orbit around the center of mass. And therefore, we cannot see the planet because it's very small, it's very faint and much fainter than the star. So we don't see the planet, but we see the star going back and forth and back and forth periodically. And this motion we can measure from the Doppler effect on light, the Doppler effect on sound, you know it well. When you have an ambulance coming towards you, the sound is more, the pitch, you say, is higher than when it goes away. That's the change of frequency with motion. And you have the same thing with the light. So when the star goes back, it's redder. When it comes toward the observer, it's bluer. And we can measure this change of colors. And what they found is that this 51 PEG star was changing color periodically with a period of a few days, only 4 days, I think. Every 4 days, you would have this curve of the motion of the star. So going back, going forth, going back, and it would reproduce very stably. So at that time, that was pretty unexpected. So they were looking for planets on like our solar system, you know, perhaps on months time scale and so on. And here they have a motion which is every 4 days. So they worked for a few months before telling the community the results and before being able to say that it's really a planet. It has nothing to do with that, to convince themselves that it was not linked with a star, but really a planet. And it was actually a bit controversial, at least by some at the beginning. And then it was fully accepted that it was indeed the first planet detection. So very strange object, a big, very big planet, a few Jupiter masses orbiting in 4 days around the star. So very, very close to the star. The other method, which is much more efficient now, is, let me see if I do that, yes, is what we call transits. So that's when a planet passes in front of its star. So this is, for instance, Venus going through the sun. That was in 2004. And you could see it from Grenoble. We had telescopes at IPAG on the parking lot. And over a few hours, you can see the silhouette of Venus going in front of the sun. So, of course, when the star is much further than the sun, we cannot see this silhouette. But what happens is that when the planet goes through this stellar area, then there is less light coming to the observer. So we see this decrease of light that lasts for a few hours. And when we see that with a very specific shape, you know, it's very steep, almost flat at the bottom, and then very steep. This is a planetary transit. And now most of the 6,000 exoplanets discovered today have been discovered by this technique. Now, this is a very small difference in luminosity from the star. So we have to do that from space because we don't have the accuracy, the required accuracy, measurement accuracy from ground. So we go to space. And the reason why most planets have been detected by this technique is that many satellites, small ones actually, or big ones to come, have been launched just specifically to detect planetary transit. So these are NASA satellites or ESA satellites. GWST is doing that as well. These CARPS and TESS are operating, and Plato is the next big European mission that will start in 2027, so 3 years from now, that will monitor tens of thousands of stars simultaneously with a cadence of 25 seconds, so take a measurement every 25 seconds for 4 years. So they will get this, they expect thousands of planetary transit to be detected from that. And this is an actual transit observed from space. And you see that here, this is the stellar luminosity, the level of the star. So we put it at 1. And you see that the decrease of luminosity is pretty small. It's a percent of a percent. So you have to be in space to be able to measure that. And this is a massive planet. If it were an Earth, the signal, the decrease of the signal would be much lower even. So what do we know so far? What have we found so far? Well, as I said, 6,000 exoplanets have been confirmed about 30 years after the first detection of 51 PEG-B. These planets are distributed in about a bit more than 4,000 planetary systems, some of which contain up to 8 planets like ours. I will show that in a moment. And the planetary masses that we are able to detect right now range from half an Earth mass, so planets smaller than Earth, up to 10 Jupiter masses, which is kind of the limit, the upper limit for planets. We know about 200 planets that have properties similar to Earth. Alors, when I say similar, it depends how you define similar, which means that they have a mass which is less than 5 times the Earth mass, and a radius which is less than 5 times the Earth radius. These are rocky bodies indeed, so we call them sometimes super Earth because they are a little bit bigger than the Earth, but they are Earth-type exoplanets. And on average, so we have detected only a few thousand planets in the solar neighborhood because we look at the nearby stars, but by extrapolation, we can tell that every star in the galaxy hosts at least 1 planet, and most of them host several planets. So planets are everywhere in the galaxy. There are 100 billion stars in the galaxy. There are 100 billion planets in the galaxy. Okay, so a few examples of planetary systems. This is one of the first planetary systems that have been detected because these are giant planets, 4 times the Jupiter mass, twice the Jupiter mass, and about the Jupiter mass, very close to their star. This is our solar system at the same scale, and you see that most of these 3 giant planets orbit closer than about Mars to the sun. So these are very compact systems, very massive planets. And that's where you have the biggest motion of the star. That's why it's easy, quote unquote, to detect. And that's why they were the first one to be detected. So a surprise because these systems are totally different from our own solar system. Then from transits, one system which was very popular is TRAPPIST-1. It has made the headlines of many medias worldwide in 2017. That's a system that contains 7 rocky planets, so Earth or super Earth. And all these 7 planets are on this scale in our system. So again, a very, very compact system. This planet, they orbit in a few days around their star. Of course, the Earth takes 1 year. Here, it's a very, very compact, multiplanetary rocky system. And the Guinness Book record of the system is the one that has 8 planets. That's the richest one we know so far. And this one is interesting because you do have rocky planets in the inner system, and you do have giant planets in the outer system. But you see that, so it's qualitatively similar to ours with a rocky planet inside and the gaseous planet outside. But the scales, again, are very, very different. You see that this outer planet has an orbital period of less than the Earth, which means that all this system, all these 8 planets, again, are contained within the Earth orbit around the Sun. So again, a very compact system. And most of the systems we find are indeed these compact systems. So part of it is an observational bias. It's easier, especially with transit, to find planets close to their star because they have a larger probability to come in front of their star. But it also means that these compact systems are very, very common through the galaxy. Okay, so I'll end with what are the current challenges we are facing and what we are looking for now that we've been progressing that much in the star and planet formation processes and the study of exoplanets. What we are looking for, what the astrophysical community is, is looking for is to detect Earth-like planets in the habitable zone, and we'll define just in a moment what is habitable zone, and search in the atmosphere of this planet, if they have an atmosphere, signatures of biological activity, that is signatures of life, essentially. So the habitable zone is defined as the distance from the star where you can have liquid water at the planet surface. And why are we looking for liquid water? Because the biologists tell us that liquid water is the medium which is favorable for the emergence of life. If you don't have a liquid, not necessarily water, but okay, let's say liquid water, if you don't have a liquid at the planetary surface, then life is probably not going to emerge. At least complexity will not emerge. And this habitable zone concept, so this is our Sun. The Earth, fortunately, is in the habitable zone, still is. Mars was in the habitable zone 1 billion years ago, but then it left the habitable zone, and there is no life actually on Mars. Maybe there has been some life in the past on Mars. Probes are sent to Mars to investigate this issue. If you have a larger star, a more massive star, it's brighter, and therefore the habitable zone is further away. If you have a lower mass star, it's less luminous, and therefore the habitable zone is closer. And the boundaries, it's because outside it's too cold, so there is no liquid water. There can be icy surfaces, and there are icy surfaces. And within the habitable zone, it's too hot, so you don't, the water evaporates, and you don't have liquid vapor at the surface. So the good thing is that most of the systems I was showing, most of the exoplanetary systems are found around stars of this type, because these are the most numerous stars in the galaxy. Most of the stars in the galaxy are most of this type rather than our Sun. And it's a good sign because, as I said, most of the planetary systems are compact systems. So many of the planets that are detected, or at least a fraction of them, are in the habitable zone. And indeed, this is an illustration. Of course, we don't see the surface of these planets, so they are just a dream of artists. But we know a few tenths of Earth-like planets, that is rocky planets, that are located in the habitable zone of their star. And coincidence or not, one of these exoplanets is orbiting the closest star to the Sun, which is Proxima Centauri, which is 4 light years away. So, okay, of course, we cannot go there. It would take, I think, 30,000 years to go there with a rocket. But we can send signals. So if this planet were to have life and an intelligent life, let's say, we could send a signal. If we take 4 years to go, so you take your phone, you say, hello, 4 years, then phone is picked up. Yes, who are you? 4 years, and so on. So it takes time. It's not a very lively conversation, but at least it's feasible on a lifetime. I mean, 4 light years is pretty close. And you see the other ones are a few tens of light years away, and so on. Of course, some are very far, 1,200 light years, but there are numbers, and we will find more and more of these Earth-like systems close to the sun. So there is a possibility of searching for life and perhaps for signals. So the challenge now is, as I showed, we don't see the planets usually. Usually we detect them because we look at the star and we see that the star is faintening, so we know there is a planet, or we see that the star is moving and we know there is a planet, but we don't see the planet. And if we don't see the planet, it means that we cannot collect the light of the planet. And if we cannot do that, we cannot analyze the properties of the planet, or at least not the atmospheric properties of the planet. What did I do there? Or my time is off, perhaps. Okay. Okay, but fortunately, with some instruments like the James Webb, but not only from the ground, also from the 4 VLT that I was showing through by combining the 4 telescopes, there are some planets for which we can get directly their photons, their light. And then we can do a spectrum. And from the spectrum, we can analyze the atmospheric composition of this planet. And this is one of the exoplanetary atmosphere spectrum taken from the James Webb that shows, can't read here, that shows water, it shows carbon dioxide, it shows sodium, it shows, well, a lot of components. That is the beginning of the chemical analysis of the atmosphere. And what we are looking is tracers of biological activity in this chemical composition. And just to give you an example, this is Venus, Mars, and the Earth. The Venus atmosphere has only carbon dioxide, a lot of it. The Mars atmosphere, it's a very thin, but still it's only carbon monoxide. And the Earth has carbon monoxide, more and more, unfortunately, and water as well. So we do detect water in the atmosphere of other exoplanets. And specific to the Earth, it has this ozone signature at about 10 microns. So it's very easy to detect from a spectrum. And this ozone comes from the conversion of molecular oxygen. And molecular oxygen is produced by photosynthetic processes, by vegetation on the Earth, actually. So if we detect ozone on an exoplanet, that could be the signature of a biological life, at least on the planet. So that's what we are looking for. It's extremely difficult to get a spectrum of the atmosphere of an exoplanet. The one I showed is a giant planet, so they are brighter, it's easier. But then to analyze the atmospheric composition of an Earth-like planet will require new instruments. And what we are thinking of is to send not one telescope, but a battery of telescopes that can be combined in space so that you get the amount of detail needed to get a spectrum of an exo-Earth. Okay, so of course, behind all these studies, there is this big question: are we alone in the universe? Are there other life forms? Where, if there is other life form, where is it? Can it be in the solar system? And it might be in the solar system indeed, because you have these satellites of some of the satellites of Saturn and Jupiter have these icy surfaces. So it's full ice at the surface. But we know that below that, there are oceans. There are subsurface oceans. And these oceans are warm, relatively warm, because the interior of the planet is warmer, like on the Earth. So it might be that below this icy surface, in these warm oceans, life or some form of life has developed, since we know that at the bottom of our oceans, for instance, especially close to hot springs, life can emerge. So there are probes that are being sent. The last one was launched, I think, a few months ago, that are going to analyze what's going on around these satellites, because you have ice, but you have cracks in the ice, and through the cracks you have geysers that send the water or whatever is in the subsurface ocean, and these probes will go there to analyze the chemical composition of this water flowing from this satellite. So maybe there could be life in the solar system outside of Earth. And of course, elsewhere in exoplanets, you've seen this habitable zone. Several planets are there. There are many, many planets. So maybe there is life or some form of life in exoplanets. Okay, so do you want me to give you the answer to the question? This is the answer, actually. Currently is that we just don't know. What we know for sure, there are many, many planets. Some look like the Earth. There are many rocky planets, many gaseous planets, many exoplanetary systems around many stars in the galaxies. Some indeed are in the habitable zone. But the emergence of life on Earth was a mix of chemistry, physics and chemistry, which is the same everywhere. So the growth of complexity, atoms getting together, molecules getting together, these are universal laws, so that might happen somewhere else. But it's also a result of random processes. For instance, at the formation of the solar system, Jupiter and Saturn formed first, giant planets. And then they start to migrate toward the star because they are accreted by the disk is accreted, and they follow the disk. And they could have gone all the way to the star and sweep up everything inside, and we would not be here to discuss that. Fortunately, as they were migrating from the star, they became synchronized in the sense that Jupiter was doing 2 orbits while Saturn was doing 1. And when you have these resonances, then it puts the planets outwards again. So it saved our life. And the other totally random process is that the moon was created from a giant impact between a protoplanet and the proto-Earth. The protoplanet is called Theia in our models. And it was not as large as the Earth, but it was a big rock, and it hurt the Earth. And then you had a cloud of dust orbiting the Earth, and from this cloud of dust, the moon formed. That was at the very beginning of the solar system. And the Earth orbit is stable only because the moon is there. If the moon was not there, the orbit of the Earth were chaotic instead of stable. And if you have a chaotic orbit, sometimes it's too hot, sometimes it's too cold, and the life probably would not have emerged as well. So what I mean is the life is a combination of, as we say, hazard and necessity, randomness and physical laws, and randomness as a big role. So that's why we are unable. It's not because there are many, many planets, some of them are in their habitable zone, that we can state today that, yes, there is life in the universe. We just don't know. We will know, well, we will know. By exploring the chemical composition of exoplanetary atmospheres, we will have some indications of whether maybe there is life on other planets or not. Okay, I will end up with this quote by Giordano Bruno, end of 16th century. Giordano Bruno was a PhD student, I would say, of Galileo Galilei. And he was writing at that time, so nearly 450 years ago, the Earth, there are countless suns and Earths revolving around their sun, just like the 7 planets in our solar system. They knew 7 planets only at that time. We can only see the stars because they are the largest and brightest bodies, but their planets remain invisible to us because they are smaller and darker. Because he wrote that, he ended burnt on a bûcher. How do you say bûcher? Anyway, he was burnt on a public place in Italy because he was saying and writing things like that. And then he was right. It was pure speculation, of course, at that time. But we now know, and for the last 2 decades, let's say, we can say that now that he was right. And then he continues saying that the countless worlds that populate the universe are no worse or less inhabited than our Earth. And that maybe in 2 decades from now, we will be able to tell whether he was right or wrong. But for the moment, we just don't know. The progress, nevertheless, that the fact that you can say that today, and you don't finish burned on a public place. So there is some improvement, at least in 5 centuries or nearly 5 centuries. Okay, and that's it. I will stop here. Thank you for your attention. If you have any questions, I will be happy to answer. And just if you are interested by this topic, you should go to Cosmocité. Have you visited Cosmocité, the new science center next to Pont-Clay and Échirolles, next to Grenoble? You can go there by tram. It's very easy. And we made a movie from this ERC project. We made an 18-minute movie, which is called At the Origin of the Cosmic Diversity, which it's more artistic than scientific, but still there is some science, and it explains, try to explain why the exoworlds and the stars and the galaxy are so different, where there is so much diversity in the universe, essentially. Thank you.
I'm not sure. Yeah, thank you so much, Jérôme. It was really fantastic talk. It answered a lot of questions I had, but I'm sure it opened up many, also for me also. And yeah, this is the time for you to to ask questions.
Hi, thank you for your very interesting talk. I wonder, here you have mainly talk about the solar system with one star, but what about the binary and ternary systems? Are they much more complicated to understand how they appear, or do we understand how they appear?
Yeah, you're right. Actually, indeed, the sun is an isolated star with its planetary system, but most of the stars in the galaxy are actually not alone. Most of them live in couples. They are binary stars orbiting one around the other, actually. And indeed, when you have a binary star, the binary star forms, again, probably through a centrifugal fragmentation of the initial cloud that form 2 stars orbiting close together. And then you still have a circumbinary disk, which surround the 2 stars. If the 2 stars are close enough, you have a circumbinary disk. And in this circumbinary disk, planets form like in a circumstellar disk. And we do have exoplanets detected around in binary systems. Now, if the stars are very far from each other, then each of them will have its own circumstellar disk and will form its own planetary systems. So the concepts and the processes are essentially the same.
You had a question, Alan?
Yes, I had a question, but I was thinking of it and I realized that it was a stupid question. Okay, so you say that if we look, so you are using the ozone molecule to track the possibility of life, but I was thinking of other molecules, and I was thinking that there is one that I vaguely remember that is only produced by life, by bacteria, I think, but I could be mistaken, it's ammoniac. But I was thinking after that, yeah, if it's true, I think it is, but then in the atmosphere, so it's so diluted that you could not even detect it, right? Because okay, just to finish, okay. So you look for ozone, but if there is life somewhere else, right? So it would not have started with photosynthesis, right?
It was really a simplification. I was just giving an example. If we find ozone, we're not specifically looking for ozone. Actually, there are easier molecule signatures of potentially biological activity in the infrared domain. Well, ozone was in the infrared, but there are other ones. And actually detecting one, be it ozone or another one, is not enough. We have to detect a number, because there was this controversy, I don't know, maybe you have followed that, of the discovery of phosphine in the atmosphere of Venus a couple of years ago by astrophysicists. And it was controversial. The detection itself was controversial because it was very low signal to noise. But then even if it is there, some chemists came and say, okay, I can produce phosphine without biological activity. So if you find one, you always get, ways to, to go around. But if we detect several on the same object, then it becomes a faisceau d'indices, which could be more convincing. So it did. Showing the ozone was just an example and maybe not the best one, but there are other molecules we can look for actually. Yeah, there was a question on the back there. Yeah.
Just for the audience on Zoom, so I saw there's about 50 people still. You can put your question in the chat and I will read it.
So thank you. I have actually two questions which are about the formation in the circumstellar disk. So you have shown pictures of the spiral shapes and concentric shapes. Is this always a signature of the spiral that it is now a planetary formation, or can it be a signature of different angular momentum in the system? And the second question was about the sequence of rocky and gaseous planets. So if you, in the solar system, the inner are rocky and outside you have gases, but we have seen that there are differences in other systems. That depends how much gas has been blown away by the star.
Okay, so the first question, what was it again? Sorry.
It was the spiral and
yes. Well, the structures we see in the disks, we try first to interpret them as without planets, So there are effects. If you have a very massive disk, for instance, the disk will be self-gravitating. So it reacts to its own gravity and not only to the gravity of the star. And when you have a self-gravitating disk, it can fragment, so form substructure by itself and fragments. And this fragment usually will form a planet. But it's not the planet that created the substructure. It's the substructure in the disk, self-gravitating disk, a very massive disk that form a planet. Usually very far away from the star. And we do see these kind of systems, that the only systems where we can have direct images of the planet, actually, because they are very far, pretty massive, so relatively bright. The other possibility to form substructure is magnetic field. We know that magnetic field is everywhere. It's on the star. There are very strong fields, thousands of Gauss compared to 3 Gauss for the sun. So they are very young, very active. And the disk also has a magnetic field. And we see that, I did not mention it at it, but in one of the disk images, you could see the disk and then a jet perpendicular. And the jet is driven, actually, that's outflow, that material ejected, because you have accretion and ejection at the same time, through the magnetic field. And the magnetic field that pervades the disk can create substructure, like gaps, for instance. Some people say gaps might not be a signature of planets. It might be a signature of magnetic magnetic forces within the disk. But still, in most systems, we still believe, especially spiral arms, in self-gravitating disks, you do have spiral arms. But all the disks I've shown are non-self-gravitating. They are low-mass disks. The mass of the disk is 1% of the mass of the star. So they are really dominated by the attraction of the star. So still, we believe most of these structures are signature of planetary formation. The second question was?
Is that for different stellar systems, we see rocky and the transition of rocky to gaseous planets at different distances?
Yes, the very first detection of 51 PEG-B became as a surprise because in the disk, most of the mass is in the outside of the disk, is in the outer part of the disk. And you need this mass to form Jupiter massive planets. So to find a Jupiter mass planet very close to the star was completely unexpected. First, because that has never been seen before, and this is not the example we have from our solar system. And secondly, because you don't have enough mass in the inner part of the disk to form this object. But very soon it was realized, and that was what I explained for Jupiter and Saturn, that when you form a massive planet, and you do form the massive planets in the outer regions, that's why you have a lot, because that's where you have a lot of rocks and gas and mass. That's why you have this thick atmosphere. Then they migrate toward the star with the disk. And this 51 PEG-B, for instance, migrated all the way very close to the star and stayed there for reasons that are not totally clear, but there is a magnetic cavity That's what I was mentioning for my project. There is a magnetospheric cavity between the star and the inner disk, and this prevents the planet to be engulfed by the star. Although we believe some planets form, migrate, and are engulfed in the stars, but this one stay there. So this massive planet, they are not formed there. They come from the outer part of the disk and they migrate inwards. Where the rocky planets, there are two schools. Some say they form where they are, and some say they form further away and they migrate as well. And for the moment, it's not decided. And we might have both, actually.
There are more questions from the audience here. And I check in the chat. No, there is nobody. Okay, maybe I have a question just for, do you always need a supernova to make the cloud, the gas cloud to collapse, or the other, like other gravitational waves, or?
Well, gravitational wave would not impact the cloud. You need a shock, a destabilizing shock on the cloud. And mostly, it can be also a massive star. The massive stars, they have these strong winds. The sun also has a wind. These are particles escaping from the star with the radiation. There are also particles. We've seen this beautiful northern lights recently in Grenoble. That was a storm on the sun that threw all these particles toward the Earth. And all the stars have these winds. But massive stars are very strong winds. And these winds, they can exert some pressure on the cloud as well. So usually it's a supernova. There are like 4 supernova exploding per century in the galaxy. So that's quite enough to propagate these shock waves through the galaxy. But sometimes it can just be a large star that destabilizes the dark cloud. Yeah.
I always thought it's a special thing for the Earth that there was a supernova exploding when our star, our solar system formed, because we can see from geochemistry, from isotopes, we can see that there is additional material that came with. So now I learned that most of systems are like this.
Yeah, absolutely.
Yeah.
We can see it on Earth. Yeah. There was a nearby supernova explosion.
Yeah. Okay, there are more questions. Okay, great.
Thank you very much for this amazing talk. I also have a stupid question. Does it matter if we're the only one in the universe? And the corollary question, is that an argument to go to funding agencies to get money for projects?
Well, does it matter? I think it matters to know where we are located. So that's why astrophysics, I mean, for me, astrophysics is a science, of course, but it's more a cultural process. You know, when you arrive in a new country, you like to know where you are, who you are going to meet, who lives there, what is the environment, and so on. So we just put it on the large scale, you know, to know where is the Earth located, where is the solar system located, are there any threats? Is the sun stable? For instance, some people say, okay, the climate is changing, but it's because of the sun. It has been changing on geological times, and we can say no, it's not because of the sun, because we monitor the sun. We have been monitoring the sun for centuries now, and we know that it is stable. So the elevation of temperature on Earth, for instance, is not due to a star, and we know that the sun, because we have a stellar structure and evolution theory, which is validated by every observation we can do. We know that the sun will still be stable for the next 5 billion years. So that's fine. Now, some people tell you also, well, it's not that, we should not matter too much about the climate change, because anyway, we can go to another planet. But that's wrong. We can tell you that's wrong. There is no planet B. If there is one, there might exist a planet B in the galaxy. Just the point is that we will never reach it. We are simply unable to reach it. We are not even able to reach the closest star, which is closer to the sun. So it's important to know what surrounds us, what are the threats on the Earth. For instance, might a big asteroid hit the Earth like it did 66 million years ago and produced a massive extinction. And we try to monitor these threats to the Earth. So I think knowing what we are, where we are, where do we come from, where we are going, perhaps, although where we are going is not much an astrophysical issue, but much more a human issue, I guess, society issue. I think it's important just to be able to locate ourselves. Now, is it important to know whether we are alone or not? I think it's more philosophical questions, and I think every one of us address the question differently with its own perspectives. And it can be religious, it can be philosophical, it can be something else, you know. Maybe you don't care, and maybe if we find life, it will not be a surprise. That is a really personal perspective. Now, is it a reason to fund agency? We don't fund agencies for that, to know whether we are alone or not. Again, we found agencies to go on other planets to better understand how the solar system formed. We found agencies, when you say fund agencies, if it is public agencies that send these satellites, observing satellites for Earth observations and for the observation of the universe, it's just to increase our knowledge again of Earth, the Earth system, and our environment. It's not uniquely, and it's not necessarily to know whether we are alone in the universe. Now, if you are talking about private companies and Mr. Musk or Bezos and so on, that's a completely different. These are my view. These are personal ambitions. You know, when Elon Musk tells you we will be going on Mars in 6 years from now, I think it's totally unrealistic and not easy to see the point of doing that. So public agencies so far have not taken this path. It's just private egos.
Okay, one more question from Jan.
Thank you. I have a more technical question. I was wondering about the detection limit for these exoplanets, and you were showing one Earth-like system in the Kepler-90 system, if I remember correctly. That was about 1,000 light years ago. So how is such an observation possible? Is this just a lucky incidence that there was a very clean area in space, or how do you actually make sure that there's nothing else in between that disturbs this observation?
Yeah, I'm not sure I understand the question, but the detection of exoplanet. So again, we look at the star, and for this system, like most of this compact system, we see these transits. So we see one transit, so we know there is a planet, and then we see another transit in the same object, and then we see up to 7 or 8 transits with different periods and so on. So we just look at the light from the star, and by monitoring the star over weeks, months, and sometimes years time scales, then you can detect all these transits. And just from the transit signature, you recover the architecture of the planetary system surrounding the star. And we have it can be at 1,000 light years. There is, the universe is not totally empty, but it's not opaque at all. I mean, the first image I showed from the James Webb Telescope, they see galaxy, you can see galaxy up to 13 billion years away, back in time and away. So the universe is now transparent. At the very beginning, it was not, but for a long time, it has been transparent. So I'm not sure I understood your question, but if you are mentioning whatever could hide stars from us, there is very little, actually.
Yeah, the question was, how far can it be able to be detected, and would it be possible to detect them even in other galaxies?
In other galaxies, yes. It's a question of accuracy of measurements.
Yes.
So you have to get enough photons, so you reduce the error bar, so you can see the transit or the radial velocity motion of the star. And that, for the transit, it's easy because we can observe very, very faint stars. And I mean, in our galaxy, pretty far away. In other galaxies, so far it has not been done, and I don't think we can do it yet in other galaxies. But we can do it for very faint stars, so we can go pretty far around the sun. Of course, we start with the easiest sample, which are the stars closer to the sun, because they are the brighter. But we can go further. Yeah.
Okay, thank you.
So no more questions. So thanks again to Jérôme to
Thank
come
you.
here, give this very, very impressive presentation, the new insights from your research. And thanks for you for coming, and thanks to the audience in Zoom for joining. Yeah. He will still be around in the afternoon. You visit a bit the ESRF and we go for lunch. So if you want to join, feel free to join. Yeah.
Thank you. Okay.
Yeah.
Maybe it was a bit long, I don't know. But in English, it's longer than in French. In French, I can go faster. I will get the key back.
Yeah.
But,
Une question en fait qui me vient en tête.
oui.
Imaginons on est sur une autre planète dans le système solaire, enfin
Ouais.
pardon dans notre galaxie quoi. Est-ce qu'on avec la technologie qu'on a actuellement, est-ce qu'on serait capable de détecter la Terre, les propulsions?
Oui, je pense qu'on pourrait la détecter. Ouais. Simplement, il faudrait, comme la période orbitale est d'un an, là, il faudrait, donc en un an, on aurait un transit, pour peu qu'on soit bien aligné.
En termes de taille, voilà.
Oui, en termes de taille, on détecte des exotères, là, déjà. Donc, on est capable de le faire, ça. Donc, quelqu'un qui aura la même technologie serait capable de le faire. Et il faudrait être patient. Et c'est ce que va faire Plateau, là. Plateau, ça a été l'ESA, il va rester 4 ans, 2 fois 2 ans, sur le même objet pour essayer de trouver justement des exotères.